All right, I've kept it from you long enough. It's time we finally cover the Bloch sphere from chapter 1.2. The Bloch sphere. Bloch is the name of a guy, Felix Bloch. I think his name is Felix. And I'd like to wait until we introduce the density matrix to do this, because it's really better to call it the Bloch ball than the Bloch sphere, and I'll explain what I mean by that. So this is where you have to try to be a bit of an artist. It's a visual representation of a single qubit. So a single qubit, this is easy to do, and it's often useful to do. It can help your intuition of what's going on. For more than a single qubit, with higher dimensions, it obviously becomes difficult to visualize. But we've been writing a single qubit state in various ways, alpha 0 plus beta 1. You can rewrite this using trigonometry in the following way, the same as in the textbook. So e to the I gamma times cosine theta over 2 as the coefficient of the zero state, plus e to the I phi sine theta over 2 as the coefficient of the one state. So this one is the global phase. That doesn't matter for us in the sense of measurement statistics. And then we have two angles here, theta and phi. So we've gone from two complex numbers, alpha and beta, describing the state, to three angles, one of which is a global phase, which doesn't matter. And then the other two are theta and phi. And you should be able to reason through this to see why this is a valid quantum state. It's normalized. Cosine squared plus sine squared will be 1. So given these angles, we can draw a sphere to represent this, known as the Bloch sphere. What we do is we include the zero state as the north pole of this sphere, and the one state as the south pole of this sphere. And then these lie on an axis, which we call the z-axis. And then the other axes will be x and y, of course at 90-degree angles to each other. And so for any valid quantum state, for any pure state, it's going to be a point on the surface of the sphere. So let's say that psi is the angle here. Psi is the state here. The angle theta will be the angle between this vector psi and the z-axis. So this is the angle theta. And then if you take the projection of this into the xy plane, which depending on how good of an artist you are is hard to do, then the angle between this projection and the x-axis is the angle phi. Okay. So usually you hear it as the Bloch sphere, and that's for pure states. Pure states are ones which we just covered, which have a purity of 1, meaning the trace of rho squared is equal to 1. Those are the ones which are on the surface of the sphere. But we know now that we could have mixed states as valid quantum states. These have purity less than 1, so these would be points on the interior of the sphere. Okay? So the radius here for pure states would be 1. For mixed states, the radius would be less than 1. You'd be on the interior of the sphere, and that is sometimes often called the Bloch ball instead of the Bloch sphere. If you want to ever calculate the Cartesian coordinates, meaning the x, y, z coordinates for a state that you have to visualize it on the Bloch sphere, the formula is as follows. So the x coordinate is the trace of rho times poly x. The y coordinate is the trace of rho times poly y. And the z coordinate is the trace of rho times poly z. This you'll prove in a homework question. I believe it's exercise 2.72 and Nielsen and Chuang. So for now, just take it as a definition, essentially. And pretty much that's what it is. I mean, we need to fix some coordinate system. We choose this one. It's easy to remember. You just need to compute the expectation value, the trace of rho times each of the Pauli matrices, and then you have the coordinates.